So first of all, let me give an overview of the different types of processes we can have. The first one is the one which will take a single instruction and then execute it, and then take the other one and execute it, and so on. So basically, there is no parallelism here. Then you can have a pipeline processor, wherein you'll have multiple stages of pipeline, and then you can execute each component of that pipeline in a shorter duration. So that is basically pipelining, and there is some amount of parallelism. And the parallelism is basically in time, because you're splitting up the entire time, and then you're making smaller components of time. That's why it's called temporal parallelism. Then you have what is called as spatial parallelism. So in spatial parallelism, you send instructions parallelly to multiple functional units. So these are called as functional units, or processing elements. So you send them to multiple functional units or processing elements, and then you operate on them parallelly. So this is called spatial parallelism. But then what is most widely used is this kind of a structure, which is a combination of both spatial and temporal parallelism, wherein you have these multiple functional units or processing elements, and then you have them pipelined. So basically, it is like the same single pipeline that we had, but then operating on multiple parallel units. So you can think of them as parallel instructions running on uh, two different pipelines. So this is of width 2, because there are two processing elements of functional units. You can think it's not a multi-core system, but then there are two parallel pipelines. So that's called as width of 2. And then the depth of 5, because the pipeline depth is 5. So this is the kind of processor that we're now going to discuss. So such a processor that I showed just now is called as a two issue, or a two wide bundle, or a two wide processor. It's called two issue processor because you can issue parallelly two instructions. So this is the first one and this is the second one. So it is called a two issue processor. In general, these kind of processors are called multiple issue processors. So you can think of this also like a VLIW processor, wherein you have these two instructions bundled and running at a time. And these can also be aligned to the functional units. So these are aligned to the functional units in a VLIW processor, but in a two-issue processor, they need not be aligned. So for example, here you have a set of instructions. You have about 6 instructions: load, add, sub, and, or, and store. So if we want to identify the dependencies, there are no dependencies here. Similarly, all of these are independent instructions without any dependencies. So you can run two of them at a time, which means that you can fetch two instructions at a time. So you're fetching two instructions, load and add, at a time in the same cycle. Then you're decoding both of them in the same cycle. Similarly, execute, memory access, and write back parallelly in the same cycle. So you cannot do more than two here, because this is a two issue processor. If you have, for example, a four issue processor, you can fetch, decode, execute four of them at the same time. So now the IPC, or the number of instructions per clock cycle, is 2. That's because you're fetching two at the same time. The IPC is the CPI is 1 over IPC, which is actually less than 1. So the number of clock cycles per instruction reduces in a multiple issue processor. So now definitely you need more hardware in order to execute this kind of instructions at the same time. So for example, if you're doing ALU and load stores in the same cycle. So if we go back to the previous slide here, you're doing a load store operation and an ALU operation in the same cycle. Similarly, here you're doing that, and here you're doing two ALU operations in the same cycle. So now, for example, if you're trying to do an ALU and a store in the same cycle, so what are the different components that you need more than what you have already? So you need to read two registers for the ALU operation. So at the max, you will need, for example, if you have an instruction like this, you will need to read two registers. Similarly, for a store, you will need to read S5. You also need to read S0 because this is for computing the address and this is for storing this data. So you need to read two again. So at the max, you need to read four of them at the same time. So you need four read ports. So that's the first task. Then if you have an ALU and a load operation, so you need again two, how many write ports do you need? So the ALU will write only once. And then you also have the load operation, which is going to write to a register again, because it's going to load the data from the memory into the register. So you need another write port. So you need two write ports. So also what you need is while the ALU is doing its addition, the load needs to have another adder to compute the effective address. So the load is going to compute the effective address by adding 40 plus S0. So you need an extra adder for that. So if you look at the hardware, this is taken from Harris and Harris. A two-issue processor, which processes two instructions per cycle, will have a structure something like this. It's very similar to what you've seen before, just that everything is duplicated in each stage. You still have the same instruction memory, but then instead of reading one instruction, you will now read two instructions into this pipeline register. And then you will have a register file into which you're going to read. Um, you'll have two extra read ports. So basically, you have read in two instructions here, and then the register file is going to give you data out. So that is four reads, and then you have parallel ALUs. So for example, if you want to do two additions or two ALU operations at the same time, an add and a sub, or add and an or, and so on. You need two ALUs here, so that's what you'll do here. Then the data memory is going to have extra ports here. So if you want to do two parallel loads, you can read in two parallel data at the same time. Or if you want to do two stores at the same time, you can do, you need to have two write ports here. So this kind of a memory is called two ported memory. So basically you have two ports instead of one. So two read ports here to be precise, and two write ports. And finally, the write back will need two multiplexers because you will have to write back two data registers parallelly, and therefore you have two write ports here to the register file. So basically everything is duplicated in a two-issue processor. If you have a four-issue processor, you'll have four copies of these things, and then you can run them parallelly. So of course it's an area overhead, but then if you need more IPC, this is one way of doing this. So an example is the very old Pentium pipeline, which had a depth of 5 and width of 2. So they were fetching two instructions, decoding two instructions. Then they had two separate pipelines. They called it the U pipeline and the V pipeline. In fact, they had a separate ID stage, an extra ID stage here, the ID2 stage. Then the EX also has the MEM stage in it, and then the write back. So this is a very old example of the Pentium pipeline, which was the first example of a two-issue processor. So now how are hazards dealt with, or dependencies dealt with in this pipeline? So if we were to have an instruction series like this, which is load, add, sub, and or, and store, where we have just created a few dependencies here. So it's a raw hazard here, a raw here, that is read after write hazard. So now in this case, you cannot have the add instruction start here because there is a dependency here. And you cannot, of course, start reading T0 in the same cycle as what you would normally do. In fact, you cannot even postpone it by just one cycle, because even in spite of having the forwarding option, you still need a stall. So these are called as load hazards, if you remember. So even if you were to do forwarding, you still need to have one stall after a load, even in a single stage pipeline with a single issue processor. In a single issue processor, you still need one stall after a load. So now in a two issue processor, this is an example of a two issue processor. You will still need to have one stall here, and you can definitely not have the add instruction issue here. So this slot will be a NOP slot. There's nothing in the slot. So now how does the forwarding work? You're going to forward T0 to the ALU of this add. So basically the ALU of this add is here, the ALU of the add, and then the forwarding data T0 is going to come from the mem stage of the load. So that's how you forward it to the add instruction here. Then the sub instruction can go along with the add because it doesn't have any dependency either on the load or on the add. So it can go parallelly here. It is going to use a different ALU in the ALU stage. So then the AND instruction here has a dependency on the previous sub. So, but that is not an issue because we are not clubbing sub and AND in the same bundle. We are, the sub is going in this particular bundle and the AND is going in a different bundle here. So that is fine. So you just have to do forwarding of data, and the forwarding is happening between the EX stage for T0 here. So EX stage to the EX stage of the AND instruction. So we forwarded T0 here. Then the next instruction in this bundle is the OR instruction. The OR instruction doesn't have any dependency on any previous instruction, so it can safely go in this bundle. Then the last instruction is the store. The store has a dependency on the previous OR, but again, that is not going in the same bundle as the OR. So the AND is here, the OR is in this bundle, and the store is going in a different bundle. So once you forward the data from the OR instruction to the ALU of the next store, you can continue without any stalls. And also remember that a store is slightly complicated to understand. Here, T3 is being used as a computation for this store. So because it's used for the computation, you need the T3 value by the ALU stage. So if T3 were to be found here, for example, then you do not need T3 by the EX stage of store, because you can directly store T3 into the memory. So you can directly forward T3 to the memory of the store. But anyway, in this example, let me just undo everything. So in this example, we are using T3 for computing this addition, and therefore you need it by the ALU stage of the store. So you forward it. Also note that the stalls always get carried forward. So how do the stalls get carried forward? You have a stall in the ID stage of this bundle, which means that the ID keeps repeating itself. So what does a stall mean? You keep repeating the same stage till you overcome the stall. So you repeat the same stage. So the second bundle is repeating its ID stage or the register. So they call it RF, which is the register file. So the ID stage is what we usually call it. So ID or the register file stage, it is repeating here in cycle 3 and in cycle 4. So that is what a stall means. So which means that the next bundle here is also going to repeat whatever stage it is in. So it is currently doing the IF stage, which is the instruction fetch stage. So it is also going to repeat that same stage in the next cycle. So whatever stage you're in, you keep repeating it till you overcome the stall. So that is what a stall does. So that is the reason why you do not see anything here. So ideally you see one fetch per cycle, but since the fetch itself is repeating here, you cannot fetch this instruction here. The reason is if you fetch the instruction here, you're going to have a structural hazard. So that's why you don't see anything here. And the instruction fetch for the next bundle starts in this cycle, which is cycle 5. So now what we have essentially done is this: there are 6 instructions, and they have we're fetching the 6th instruction in the 5th cycle. So essentially it is 6 instructions in 5 cycles, and therefore the IPC is 1.2.